rectangular shafts. Okay. Now this is, however, not that trivial. Torsion of rectangular shafts is way harder than torsion of circular shafts, and this is why. So when you have circular shafts, we have this property, nice, really nice property, that plane sections remain plane. What it means is that when you apply a torque, if you look at any cross section, like say this one, under the effect of this torque, let's call it T, this section remains plane. It will not deflect in this direction. There will be no deflection in the direction normal to it. So it's a nice thing. It won't induce stresses in the direction other than along its own axis. Now, if you have a rectangular shaft, however, plane sections do not remain plane. So for a rectangular shaft, plane sections get distorted. And this is really hard to draw sometimes. So if you have a shaft like this is a rectangular shaft, and you subject it to, let's see, a torque like so. So what will happen is, let me try to draw this. So this face is distorted. And it's actually also out of plane. If you have something which is soft, which I don't have here right now in the class, you could actually do the experiment. If you twist, those uh, the sponges you get which you use to clean utensils, those things are soft and they are also rectangular in cross section. If you take that and twist it, you'll see that plane sections don't remain plane. They get distorted. That's where the whole uh, calculations of the stress becomes very hard. So this makes it hard. So the derivation for of tau max, the twist, is beyond scope of this class, okay, because it's kind of harder to come up with equations. However, what we'll do is we still need to do calculations for sections which are not um, circular, right? So what we do is we basically have these tables which we can use. So I'm going to show you a table. It's not that the tables are kind of simple though, and so there are like people who have done this calculations for different uh, geometries, length and width, and they have a table, and we can just use the table to figure out what is the maximum stress and the angle of twist. Okay, so here is the table. One sec. Okay, here is the table. Okay, so I'll show you how to interpret the table. Uh, if you have a shaft like this, and let's assume that subject it to a torque this way, and I'm going to put some dimensions. So let's say that the thickness is C, this length. Okay, you can see that this length is actually parallel to the axis I've shown. This length is B. Okay, then here is a formula for the maximum shear stress. It's the torque divided by alpha times BC square. Okay, so note it's very important that you know what B and C is. B is going to be the thickness normal to this axis, and C is going to be the width. So you need to have this picture in mind before you can use this formula. There's a parameter alpha. That alpha is over here. So for various B and C, you can compute the ratio B divided by C. Once you have that ratio, you can compute what alpha is and then get the value for the maximum torque. Similarly, there's a formula for angle of twist, theta. And theta is PL divided by beta BC cube times G. Okay, there's a factor beta, which again is in this table. Okay, so you compute the ratio of B to C, then compute beta, and then you'll put it in the formula and compute the angle of twist. But it's important, as I said, know what C, B, and L is. Without that, you're sort of lost. You can't do much.